Waylin, all right. So Waylin, are you section?
Section 2.
Okay, you section 2. Waylin. All right. Okay, Lim, the first name, Lim Weizi. Is it the same?
Yes, doctor.
Okay. All right, you are coming. Okay, thank you very much for noticing me. Okay, sometimes I forgot. Okay, so yesterday we learned about normalized differential equation where we convert from the standard differential equation into normalized differential equation. So let me repeat again. What is actually mean by normalized? Okay, let me ask Emil Zikran bin Badardin. Emil Zikran from section 8. Are you there?
Hello?
Yes. Are you Emil Zikran?
Yeah. What was the question?
The question is, what is the definitions of normalized differential? Normalized.
Dimensionless.
Yes, perfect. So Emil, you got 10 points. Thank you very much for your quick answer. Okay. So remember that normalized is the synonyms for dimensionless, or we call as a unitless. For example, like Renault number, like Weber number, like Stoffel number, like Mach number, Euler number, all these is called a dimensionless common parameter. Okay, so for today, we are going to cover, and then yesterday we learned about a little bit of internal flow. Remember that the flow inside the pipe, okay, we call as the internal flow. So what is the internal flow? It is mostly governed by the viscosity, as you can see in this slide. Okay, so when this is involved of viscosity, definitely the common dimensionless parameter that significant in this study is Renault number. All right, so Renault number is rho Vd or rho Vl over mu. Mu is the viscosity. That is why you can see this viscosity effect is the dominant factor in the internal flow. All right. So when we involve the Renault number, definitely the Renault number will tell you whether the flow is turbulent or laminar based on this value, which is when the flow inside the pipe less than 2000, it's considered laminar. All right, when it is less than 1500 in the white channel, this is the shape, square shape or rectangular shape, we call as the laminar flow. Okay, example of laminar flow such as our blood, all right, through the veins. So at height, sufficient height Renault number, the turbulence will occur. Okay, so here let's continue into the internal flow. Okay, let's say this is the pipe. Okay, inside the pipe there is the inlet. You can see here. Okay, give me seconds. Let me set up. Okay. Inside the pipe, Okay, let me change the work area a second. Okay, inside the pipe, okay, this is the cross-sectional area when you look at from here. Okay, of course round. Okay, this is the inlet, and this is outlet. All right. So inside the pipe, we have a different profile. We call as a different velocity profile. So what mean by profile? This is the profile. Okay, you can see this one. This is what we call as a velocity profile. Okay. So why we call a profile? Sometimes velocity will have different profile. You can see this profile different from the middle. The middle different at the outlet. So all this profile has different characteristic. That is why we need to investigate and learn why this profile change when we have different kind of flow. For example, laminar or turbulent flow. Okay. So, the developed laminar flow where the velocity profile cease to change in the flow direction. Okay, so this is we call as a developed. That means it is fully developed, 100% developed. The velocity will not change. The velocity profile will not change over time. So, do you know why and how the velocity profile is created? How this is formed? Okay, you can see here. This is our velocity profile, right? Okay, and then this is inside the pipe. Why this is forming like this? Okay, why this is formed like this? Anyone would like to try?
Due to friction.
Due to?
Because of the viscosity.
Viscosity
Okay.
friction in the plates.
Okay, Najmul, your section.
Yes, doctor.
Your section. You are section.
1, doctor.
Okay, thank you very much. You got 10 points. Okay.
Total of 25 points.
Pardon?
Shouldn't I have total of 25 points?
Okay, yes, the point will help you later on. Okay,
Alright.
this is the pipe. Inside the pipe, definitely we have the wall friction. Okay, this wall friction will cause the water flow to be like this. This is what we call as a velocity profile. Okay, why this is happening? Okay, let me show you. Okay, at the wall layer, due to the viscosity effect, okay, this water will stick into the wall, okay, because of the roughness. So the velocity is low here. Away from the wall, the velocity is quite large until at the center we call as a maximum velocity. When the velocity approaching the wall, due to the viscosity effect that will hinder the flow, and we have the friction factor, okay, the velocity near the wall is almost zero. That is why we have the connecting dot here. Okay, everyone understand why the velocity profile coming from?
Doctor, can I ask a question?
Huh?
I have a question.
Okay, what's your question?
Does it also assume that the viscosity within the fluid layers is less than the viscosity between the fluid layer and the surface?
The viscosity is constant. Okay, remember that the viscosity is still the fixed constant for the property. But the difference here is actually the velocity. The velocity will be affected by the locations of the flow. Okay?
Isn't the viscosity between the liquid and the wall one and between the liquid itself, the internal viscosity is different?
The internal viscosity.
I mean the intermolecular force of the liquid. So isn't it different?
Okay, it is not different. Dynamic viscosity is still the constant. Okay, but the
Okay.
difference, this is the wall. This is the wall. Okay, and then we have the friction or roughness. Okay, due to the flow, you can see here the flow here, and then the flow coming to the near the wall, it's stuck. Okay, stuck because of this roughness. Near the wall, what do you think? The flow
The velocity zero.
zero. Okay, okay.
Yes.
Because of this will the second layer will try to push the third layer from moving. It try to hold. Okay, this one's moving away.
Yeah.
Okay, this is what we call a velocity profile for the parallel pipe. Okay, for the pipe, this is like this. Okay, so this is what the velocity profile coming from. So in a fully developed laminar flow, the velocity profile cease to change. Don't want to change. So the velocity profile at time 1, the same with time 2. Okay, let's say this is the time 1. And time 2, 3, and 4 are, I think, let's say this is assume the same, yeah? Okay. That means the same in terms of the velocity magnitude, and the direction. This is time 2. Okay. This, you can see, this profile will not change when this is considered fully developed. It is 100% matured. Okay. You can see here. Developed laminar flow. This is the profile. Okay, away from this pipe also the same. Okay, this is cease to change, will not change at all when this is considered as developed laminar flow. Okay, and in the entrance region, this is what we call entrance region of laminar flow. The velocity profile change in the flow direction. Okay, this is true. You can see it start to change. The velocity profile initially like this. Okay, after few seconds, it become like this because this velocity profile going to transform from the undeveloped to the fully developed laminar flow. Okay, it want to transform this shape into this. This is matured shape. Okay, so maybe like this. Okay, this is velocity profile. Want to change. Okay, until become like this. This is the final version, complete version. Okay, after this, still the same. Okay, so at time 1, time 2, time 3, and time 4. Time 3 and time 4 is fully developed laminar flow. It will never change. Okay, idealized flow from the reservoir begin at the inlet as the uniform flow, right? Sometimes we call as a uniform flow when it is like this. This is the pipe, this is the flow. Okay, the viscosity near the wall is neglected. Okay, this is what we call as a uniform flow. You can see it is parallel. Okay, the length is same, we call as a uniform flow. Basically, this is just a introduction lah for the flow in pipe. Okay, because you need to understand this when you go into the major and minor losses in the pipe. Okay, once you understand this fundamental concept, definitely this will help you to master the next section, which is the major and minor losses. Okay, where we use the Moody chart. Okay, I believe maybe some of you repeat from the previous section. Okay, you learn the Moody chart. So in order to understand more, please focus on this. This is the very important concept. Okay, about the flow. So the viscous wall layer grow over the inviscid core length Li. Okay, so in here let's introduce you into the viscous wall layer. Okay, you can see this is the entrance length. Alright, this is the pipe. Alright, inside the pipe we divide into two. This is the entrance length and this is the developed laminar flow. Inside the entrance length in this section we have, okay, what we call as the inviscid core length. Alright, inviscid core length Li. Okay, after this is the rest is the profile development length. Okay, so inside here we have the viscous wall layer. Okay, that means the viscous effect is dominant in this region. For the inviscid core, the viscous is not significant. Okay, you can see here they separate, make it like this. Okay, so what happened is that, okay, this when the flow continuously to flow, this viscous wall layer will close the gap, try to close the gap. Alright, you can see until there is no more inviscid core. So that is why the viscous wall layer will try to close the gap, okay, when the flow continuously flow through the pipe. So the developed profile due to the viscous effect until the developed flow is achieved. Okay. Right. So the entrance length equation for the laminar flow in a circular pipe with uniform profile at the inlet. Okay, when the Reynolds number for the laminar is 2000. Okay, this is the how to get the Li. Sorry, this is Le. Okay, this is how to get to measure the Le. Alright, when this is as a laminar flow, the formula is Le over D equal to 0.065 Reynolds number. Okay, this is when you consider as a laminar flow. Okay, when the flow is laminar, which is around 2000, you just substitute the value of Reynolds number, multiply with this number, and then multiply with D, you will get the entrance length. Okay, this is, you notice that this is dimensionless. That is why previously we learned the normalized differential equation, we learned the similitude study, dimensionless quantity, because after this we're going to explore more on the dimensionless quantity. So you can see Reynolds number is dimensionless, L over D is dimensionless. Okay, so dimensionless will tell us the ratio of our interest. For example, LE, we want to find LE. What is the distance here? The entrance length. So simply 0.065 multiply with the laminar Reynolds number, multiply with D, the diameter of this pipe. Okay, this is the based on the theory, okay, and the experiment discovered to get the entrance length. Okay, for the laminar flow in the high aspect ratio channel, okay, this is for the pipe flow. This is the pipe. Okay, and this is for the channel, which is like this. Okay, so when the flow is laminar flow, Le over H is equal to 0.04 Reynolds number. Okay, this is what we call as the Reynolds number to get the entrance length. Okay, basically this is more on the theory. For the large Reynolds number, okay, when the large Reynolds number is very large, which is around when we consider it is a very large Reynolds number, please remember that when the Reynolds number is large, the value of Reynolds number is around 10, is more than 10 the power of 5. Okay, this is what we consider as a turbulent. Okay, so in order to get the entrance length, okay, this is what happened when the flow become turbulent. Okay, we have different profile. Previously, this is laminar. Remember, this is for laminar. Okay, and this one, when the flow is very high Reynolds number, this is become turbulent. Okay, remember the turbulent is a chaotic flow. It is disorderly flow. Okay, inside here we have an additional entrance. We have the many entrance. For example, we have Li. Okay, in visit core length we have LD. Development length we have the entrance length L. Okay, as well as the development turbulent flow. Okay, you notice that the development turbulent flow with the laminar flow is like this. The developed laminar flow, the profile is like this. For the turbulent developed flow, this is the profile. Okay, so inside here, how to get this parameter, how to get Li, how to get LD, how to get Le. Simply the equation is, okay, Li, we're going to use the dimensionless parameter quantity as well. Li over D equal to roughly equal to 10. Okay, for LD development length, okay, over D, which is roughly around 40, and for LE entrance length over D, which is roughly around 120. Okay, this is the ratio. Basically, this is more on the theory lah. Okay, basically, okay, I think that's all. Okay, we finished about the internal flow. What I would like to highlight basically, inside the pipe we have the laminar and turbulent flow. Alright, so inside laminar we have the entrance length, okay, and the development laminar flow. Okay, so for the turbulent, inside the entrance length we have the development flow and in-visit core length. Okay, so this is the profile, and then to get the characteristic length or to get the LE entrance length, it is simply, okay, LE untuk just for laminar, LE over D is 0.065 Reynolds number. Okay. Okay. So this is more on the theoretical part lah. Alright. You can read this one. Okay. This is the supplement for you. Okay, but the most important thing you need to master, you need to understand is the profile. Okay, the turbulent, what happened inside the turbulent. We have the non-uniform flow. Okay, we have the in-visit core length. Okay, until the flow become matured flow, it will turn into the developed turbulent flow. Okay, this is just a definition. Okay, that we proceed on the laminar flow.
So this one you didn't give yet to us.
Yes, it's okay. Just listen carefully. I will upload later on. Okay. I will upload including the fill up version. Okay. So for this one, let's start with the laminar flow. Okay. Previously we learned about the internal flow. We learned about the normalized differential equation. That is the basic form. Now we go into deep of laminar flow in a pipe. Okay. So laminar flow in the pipe. as you all know that the laminar is the flow is the orderly manner flow. All right. So in the laminar flow, we are going to investigate the incompressibility steady developed laminar flow in the pipe. Okay, when you can see here, this is a developed laminar flow. That means we are not consider about the entrance length. Okay, in the inviscid core length, we are not interested into that. We are interested into the developed laminar flow. So what mean by developed laminar flow? Anyone would like to try?
It means like it's never
Pardon? Can you repeat?
complete flow. It's like never change after fully developed laminar
Yes.
flow.
Okay, perfect. So remember that the velocity profile cease to change, never change at all. Okay, so your name Aina from section?
1.
Okay, Aina Zafira, 10 point for you. Okay, thank you for your response. Okay, that is correct, and I can see that you understand about the different kind of flow. Okay, so for this case, we focus on the developed laminar flow. So inside the developed laminar flow, focus on this part. Okay, how to investigate about the quantity. For example, like I'm interested into the pressure, I'm interested into the shear stress. Okay, how to get the radius when the velocity is 3 meter per second. Okay, so we are going to use the elemental approach. Just simply we cut out one portion of the flow and we form like this. This is what we call as a elemental approach. So an elemental approach is the infinitesimal control volume into which from which the flow fluid flow. Okay, that means there is the flow into and out of the control volume. Just consider this is the control volume. Okay, so this elemental approach, we use the Newton's second law. Okay, which is summation of force is equal to mass multiplied with acceleration. Okay. Let me open the lecture note. Okay, let me show you the derivations a little bit. Okay, this is the flow. Okay, this is the pipe flow. Remember, this is a fully developed flow for laminar flow, and we have the inclination angle theta. Okay, this is the triangle. Okay, this is the theta, and this is the DH, the direction. You notice that this is negative DH because it is pointing downward, and this is the X. Okay, because this is the axis of X. Okay, this is the axis X. Let's say this is Y. Okay, so since velocity profile does not change in the X direction, okay, means this is fully developed flow. The velocity profile does not change. The cease to change, never change. The momentum flux in equal to momentum flux out, and the resultant force is 0. Simply F equal to 0 lah, right? Because there is no momentum. So no acceleration of the mass element, resultant force is 0. So summation of force equal to 0 because the velocity profile in the x direction never change. So we can put this way. Okay, the summation of force in the x direction equal to 0. Okay, no acceleration. And the direction is in this direction, positive. Okay, you can see this direction. And then I would like to highlight again this one. Alright, I take out from this. This is theta. This is the inclination. This is the pipe inclination. And this is negative DH because the height, this is the depth. Okay, below from the going downward, it is negative, and this is the direction of flow, dx. Okay, from this triangle, let's form the summation of force based on this, okay, elemental approach. You can see here. Okay, let me explain. When we try to cut out this form, okay, we have the shear stress. You can see the shear stress acting at the wall. So tau multiply with area. This is tau A. Area is 2 pi r multiply with dx. Okay, area here is 2 pi r multiply with dx. I believe you understand the concepts of the shear stress. Let me explain clearly. Okay, this is like this. Okay, 2 pi r is the circumference. Okay, this is circumference 2 pi r. Okay, now you understand the circumference. Multiply with dx. This is distance here, dx. So what you're gonna have? You're gonna have this area, right? Okay, I don't know how to write. Okay, this is the area, okay, surrounding this one, this area. Okay, this area, closing all this. Okay, so area is 2 pi r dx. This is the shear stress area. So tau A is this. Tau A is the same here, yeah? And the direction is reverse the flow. The flow is like this. And this is shear stress acting in this direction. Okay, so and then we have the normal force, which is P multiplied with the area, which is force equal to P multiplied with A. Pressure multiplied with area, which is area of this circle, pi r squared. And this form also the same. This is F. Let's say this is F1, this is F2. Multiply with the area. So YF2 is equal to P plus dP. Okay, let's say this is a point. Okay, let's say. Okay, let's say this is the point 1 and this is point 2. The pressure at point 1 and pressure at point 2. Okay. So, the delta P basically pressure 2 minus pressure 1. Okay, so from here, in order to get the F2, okay, P2 is equal to delta P plus P1. That is why you can see F2, or simply we call as the this is P2, okay, multiply with the area. Okay, now you understand, everyone, do you understand about these derivations? Why this is P plus dP? Because this is from this one. Okay, from this one, let's make the summation of force equal to 0. Okay, so from here, let me start the derivation. Okay, what do we have the force here? Okay, let's start with this. Okay, we have the pressure multiplied with the area. So P pi r squared. And then this is positive and this is the negative, minus P plus dP, the change of pressure, pi r squared. And then we have this one, shear stress, minus tau 2 pi r dx. Okay, and then we have one more. Anyone? Is it complete now? Okay, Morteza Yuriski, are you there? Omar Ehab Saad Ali. Are you there? Okay, no. Muhammad Robian Nando Putra Awi. Are you there? Okay, not coming. And we have a Rizky Zulin Pratama. Are you there?
Doctor, can I try?
Doctor, I'm here, doctor.
Your name is?
Risky, doctor.
Okay, yes, coming. Okay, I would like to ask you, is it the equation complete now for the summation of force equal to 0? Rizky?
Yes, doctor.
This equation complete or not complete?
I think no, doctor.
Okay, why?
Doctor, can I try?
Okay, yes, you can try.
My name is
Your
Dr.
name? Your name, please?
Haytham,
Haitam. Okay, Haitam. Section?
section 1.
Okay, Haitam. Okay, what's we need to add? Huh?
To add the angle, right? The theta.
Eta? Why we need to add the eta?
Because we are mentioning in dx.
Okay, you want to X this one? I think because now we consider the direction in this direction. No need to add the theta. You can see? If we
Actually,
consider,
there is another force left behind.
Okay, what's the force?
The friction.
Is actually gamma pi square dx.
Yeah.
Yes, gamma pi square dx, and also for the x direction sin theta.
Okay, correct. We have Shahidul. Your name Shahidul Islam.
Yes, doctor.
From section
2.
Okay, Shahidul Islam. You got 10 points. Okay, thank you very much. Okay, we have gamma pi r squared dx. What is this? Anyone would like to try?
Viscous force, doctor.
Viscous force. No, this is not viscous force. This is very basic one. This is control volume. Anyone would like to try? What is this? Gamma pi r squared dx. Let's try Nur Khairina Alia. Are you there?
Yes,
Nur,
doctor.
Nur, your name, please?
Kairina Alia.
Okay, Khairina Alia. Okay, what is this, Khairina? What is this?
Sorry,
Ada?
doctor, I don't know.
Okay, it's okay. Anyone would like to try? I give 10 points. This is very simple.
Is it weight
Apa
gravity
soalan ni?
Pardon?
Apa
weight lah.
Apa? Okay, I heard someone tadi cakap apa tadi?
Weight.
Okay, wait. Your name?
Nor Asmadini.
Nur Asma Dini from section?
Section 2.
Okay. Nur and you are ya? Okay, Asma Dini. Okay, you get 10 points. Okay, correct. This is the weight of this control volume. Okay. So what is the formula of weight? Weight is equal to mass multiplied with gravity. Okay, mass. What is the mass? Mass equal density equal to mass over volume. So mass is volume multiplied with gravity. Sorry, I confused. The volume multiplied with the rho. Okay, so we can replace the mass with the rho v G. Okay. So weight is equal to rho Vg. I believe I explained during the buoyancy force. Okay. Rho Vg. Okay. Gamma. What is gamma? What is the formula of gamma?
Rho times G.
Yes, rho times G. Can we replace rho G with gamma? Yes, weight equal to gamma multiplied with volume. This is the symbol of volume, yeah. So, where is the volume? This is the volume. Okay, volume of what? Can you see? Okay, gamma multiplied with volume. Pi r squared. Pi r squared is what? The area, right? Area of cross-sectional area. Pi r squared. Dx is
The height.
the height. So, what you get? You get the cylinder, the volume of cylinder. So this is the volume of cylinder, you can see. So this is the volume. Gamma multiplied with the volume is the weight. Okay, so we have the weight. Weight is the force. So we have to consider the weight inside our equation. So the weight, what's the direction? The direction of weight is in this direction. Okay, you can see this is the weight, always toward the gravity. And then when we consider it is in the x direction like this, let's make the weight in this direction. Okay, so gamma pi is positive or negative? The weight here.
Positive.
Positive. So because it is the same direction like this. Positive. Okay, I think the wrong pen. Okay, positive. Gamma, what is gamma? Pi r squared dx. And then we need to add one more. What is it?
Sin theta.
Sin theta.
Sine or cos? Sine. Okay, we need to add sine theta equal to 0. Because why? Because this is angle, inclination. In order to get this in the same direction, we have to sine with the theta. Okay. So from here, let's expand p pi r squared minus p. Let's expand pi r squared minus dp pi r squared minus tau 2 pi r dx plus gamma pi r squared dx sine. Okay. So sine, where to get the sine theta? From here. Sine theta equal to SOH, opposite over hypotenuse. So opposite is negative dH over hypotenuse is dx. So we can replace negative dH over dx. And then we can cancel out dx with dx. Okay. And then we can continue to cancel. So this we can cancel. This we can cancel. So what we have? Negative dp pi r squared minus tau 2 pi r dx plus gamma pi r squared. Okay, this is negative. Should be negative here. Okay. Negative dH. Okay. So what we need to do? We need to make the tau to be the subject. So we can move this one. This is equal to 0, yeah. So we can make this one move to the other side. Okay. So tau 2 pi r dx equal to negative dp pi r squared plus okay, negative gamma pi r squared dh. Okay. Alright, so this. Okay, let me check first. Okay, this is correct. This is correct. Okay. So now we can simplify the equation. We can simplify the pi, and pi. We have to simplify the r, and this r. Okay. So what do we have next is 2 tau dx equal to negative dp r, kan? R, we have r here, minus gamma r dh. Okay, so we can do the factorization. Negative r dp plus, okay, gamma dh. This is 2 tau dx. Okay, definitely tau is equal to negative r over 2. Okay, this d we can factorize as well, d over dx. This is dx from here, and pressure plus gamma h. Okay, you can see the d differential for pressure is valid. The differential for gamma or differential for h? Anyone? Which one is correct? D gamma or dh?
DH.
Okay, what is okay? Why h? Why not gamma?
Because H will vary. Height will vary.
Okay, yes, perfect. The h will vary, but the gamma is
Constant.
constant. Perfect. You understand? Okay, if the car, your section.
Section 1, doctor.
If the car, thank you very much. You got 10 points. Okay, that is why we can factorize the d. So simply tau, okay, equal to negative r over 2 d over dx p plus gamma h. Okay, so this is what we learned previously. And another equation, we know that the tau basically is negative mu du over dr. This is from the equation 1 section. This is chapter 155. This is the definition of tau. Tau equal to mu du over dr. Okay. Or tau equal to mu du over dy. Okay. This is the same, yeah? Okay. Anyone? Do you know why this is negative, this is positive? Anyone would like to try? Is it the same or different? Okay, I can say here, tau is a negative u du over dr is equal to mu du over dy. Okay, anyone, is it correct or otherwise? Anyone? Why this is negative? Why this is positive? Anyone, are you there? Okay, let me call. Okay, Najmul.
Because I think the tau is the shear is in opposite direction for the motion.
Okay.
The direction is in opposite as well.
Opposite direction. Okay. Anyone would like to try?
I think, doctor, because the entrance is equal, the entrance fluid is equal the leaving fluid, right?
Okay lah. I let me draw.
Is it because the viscosity is opposite to the flow?
I know. Okay, let me show you. This is the pipe. Okay, this is the center of the pipe. Okay, and this is the R. We call as the R naught. Okay, R from the wall. This is the this is the total R. Okay, the R from the center to the wall. Okay, why? Where is the Y? Y is here. This is Y. The Y start from the wall, yeah, and the R here start from the center. This is the R. Okay, what is the equation? Okay, you can see R. How to get the Y? Y equal to, how to get the Y? This is simple mathematics. Y equal to, how to get Y?
R dot minus
R naught
minus R.
Minus R.
R. Okay, can we try to do differentiate both? We do both differentiation. Okay, dy equal to dr naught minus dr. Okay, which one is constant? R naught, R or Y?
R naught.
R naught is constant, fixed, right? So when we differentiate constant, what we get?
Constant.
We got?
The zero.
Zero. So what the final version? Dy equal to negative dr. Can you see this one? This is dy. Dy, when we replace dy with dr, we have to put negative. Can you see we have negative? Anyone? Do you understand now?
Yes.
Yes, doctor.
Okay. So from here, okay, we know that tau in the relationship to the r is negative mu du over dr. Okay, can we equate? Yes, we can equate. You can see we can equate them together. We can equate this one because both are tau and tau. We can equate them together. Okay. So we can equate. Let's equate them together. Okay. So negative mu du over dr equal to negative r over 2. This one, yeah. Okay. D over dx p plus gamma h. Okay, I try to equate them together. Okay, like this. So from here we can see negative and negative we can cancel out. Cancel. Okay, and then we have the dr. You can see we have dr. We can move to the other side and rearrange mu du. Okay. Sorry. I want to move mu as well to the other side. So I will have du only equal to, okay, r over 2 mu d over dx, okay, d over dx p plus gamma h dr. Okay, since the, okay, after this we have du and dr, we can do the integration both sides, okay, in order to get the velocity vector for the developed flow here. Okay, when we do this, we know that integration of du, this is the velocity, we got the u with the function of r. Okay, from here, okay, this is d over dx, okay. this is the constant because it is fully developed. Okay, velocity profile will not change. Okay, the only have is this one, the R will change. You can see this is dr. Okay, so d over dx. Okay, 1 over 2 mu p plus gamma h integration r dr. Okay, so I try to integrate. I will have u the function of 1 over 2 mu d over dx pressure plus gamma h integration r squared, okay, over 2. This is from r0 to r, okay. So this is r0 from r. Okay, this is 2 multiplied with 2 is 4. Okay, 1 over 4 mu d over dx p plus gamma h and r squared minus r0 squared. Okay, so the final form of the velocity distribution is parabolic. You can see this is the parabolic form. Parabolic form. Because we have radius minus radius. Okay, so sometimes this equation we call as a Poisson flow. Okay, this is the laminar flow with the parabolic profile in the pipe or between the parallel plate. Okay, you can see this is the final version. Okay, after I derive for you, this is the velocity distribution. The velocity u is the velocity will vary with r. Okay, change the r will have the change in u. So 1 over 4 mu, this is the pressure drop, yeah, dp, pressure drop, dp over dx, the pressure drop over distance. Okay, multiply with the parabolic function. This is r squared minus r0 squared. Okay, so from here, okay, in order to get the average velocity, sometimes when we do the calculation, it's difficult for us to get the u. We sometimes use the average velocity to ease the calculation. So we know that the continuity equation q equal to av. Q equal to av for the incompressible flow when the density is constant. Okay, so here q equal to 1. Okay, q equal to av. Okay, so q here, okay, we try to substitute. Area is pi r squared and ur, okay, q equal to av. Okay, we try to substitute this one, okay, into this form. Okay, this is q equal to, this is a and this is b. Okay, we do the substitution. Okay, so ur, we substitute back this one, ur into this equation, and finally we get this, the average velocity to be this one. Okay, so for the horizontal part, the pressure drop is as follow. So in order to get the pressure drop, delta P is equal to 8. This is the equation, mu V L over R0 squared. Okay, basically this is derived from this one, yeah. Okay, when you try to derive this one, for example, this is B. Okay, this one V equal to negative R0 squared over 8 mu. This is d p plus gamma h over dx. Okay, this one we can replace with dp over dx. Okay, when the horizontal pipe. Okay, that means there is no change in height. There is no height. We consider there is no change in height. dh equal to 0. So v equal to, okay, this is the pressure drop. We know already it is drop. Negative cancel out. R naught squared over 8 mu. Okay, pressure drop we can change with this one over dx we can replace with L. So how to get the pressure drop? The pressure drop is simply, you can see 8 mu BL over R naught squared. This is the same with this one. Okay, do you guys understand? This is just a concept, yeah. I hope you can grab this one. Okay, another form of the pressure drop is 2 tau L over R naught. Okay, this is another conversion lah, simply the conversion. Okay, and then we learn about the next term, the friction factor. Okay, remember that last class I talked about the roughness, pipe roughness. So in terms of the dimensionless quantity for the pipe roughness, we call in terms of friction factor. Okay, this is the dimensionless factor. So you can see dimensionless wall shear valid for both laminar and turbulent. So this friction factor valid for both laminar and turbulent. So this is the equation F equal to tau naught over 1 over 8 rho v squared. Okay. Okay, this is the shear stress at the wall. For laminar flow in the pipe, where the friction factor equal to 64 over Reynolds number. Okay, this is for the laminar flow. In order to get the friction factor, simply substitute the value of the laminar flow, okay, into this equation, as well as the head loss. Okay, this is the dimension of length, head loss. Okay, 32. Okay, this head loss is directly proportional to the average velocity for the laminar. So this is for laminar head loss equal to 32 mu LV over gamma D. Okay, basically to come into here, this equation, lots of derivation. For this is the Darcy-Weisbach equation, valid for both laminar. Okay, this is the equation, the pressure drop over gamma equal to head loss basically. So F L over D V squared over 2G. Okay, it's okay. Later on, I will give you the complete version of this. Okay, I need you to study and remember. Okay. Okay, I think we take a rest, 10 more minutes, okay, before we continue about the turbulent flow in the pipe. Okay, we take a rest, yeah.
Doctor.
Okay, everyone, are you there?
Yes, doctor.
Okay, let's finish early. Okay, so I want to cover the turbulent flow. Basically, this part more on the theory. Okay, I prefer to work on example on how to calculate the major and minor losses. Okay, so for this part, we move on from the laminar flow into the turbulent flow in a pipe. So, develop turbulent flow in a circular pipe is of interest, is practical application. Okay, most flow is turbulent flow. Okay, so laminar flow have been seen in Reynolds number of 40,000 in the pipe flow. So this is the in order for you to understand more the difference between the laminar and the turbulent flow, you can watch this video. This explain clearly what is laminar and what is turbulent flow. Okay, simply the turbulent flow is a chaotic flow, disorderly manner flow. So the flow, when we talk about the flow, we normally express in terms of velocity. The velocity in the X, Y, and Z direction would be like this. This is fluctuating flow. This is in the X direction. This is in the Y direction. This is in the Z direction. The velocity is like this, fluctuating flow. Alright, this is what we call a turbulent flow. It is not straight. Okay, it is not linear. So it is kind of difficult to solve when it is like this. So what we need to do? We need to, okay, let me open. Alright. So we need to average them in order to get the velocity. So it is hardly to calculate when we have this kind of phenomena. So what we need to do, we need to average all the velocity here. How to do the average? U average is equal to 1 over time. That means we do the time average. You can see need time average quantity. Integration from 0 to total time. Okay. U of t dt. Okay, that means we can get this, the straight line. Okay, when we do the averaging. So, in order to do the averaging, the differential equation that must be solved to provide us with the time average. You can see this is over t. Okay, which is over time, differential over time. So we need to use the differential equation, okay, to get the time average velocity, because the velocity is fluctuating flow. Okay, so the fluid particle move enter the neighboring layer. Okay, for example, this is the layer. This is the fluid particle entering this region. Okay, moving with the higher x component. This is x component. Okay, this is y component, and this is z component. So this is z component. Okay, when the particle move with the higher x component velocity, thereby providing the retarding effect on the layer. The fluid particle that move to the layer tend to accelerate the slower moving fluid. Okay, for example, we have another fluid here. Okay, this is the fluid. Okay, the fluid is still in the motion, and then this particle, the turbulent particle, okay, move in this direction. It will, okay, it will tend here, tend to accelerate the slower moving fluid. Okay, so the x component force that result due to the random motion of the fluid particle passing to the incremental area dA. This is the dA will be like this. Okay, this is the dF. Okay, negative rho v dA u. Okay, v, remember this is the velocity in the y direction, and u, this is the velocity in the x direction. You can see this form, this symbol represent the fluctuating. Okay, this is the random motion. Okay, where u is the negative change in the x component due to the entering into the area. Remember that when we have the area, okay, applying the Reynolds transport theorem into the page, into the control volume is negative. Okay, out of control volume is positive. That is why when it is into the control volume, into the cross-sectional area, it is negative symbol. Okay, so from here, let's divide all this with area. You can see dA and dA. We can cancel out this one. Okay, what we have here basically dF over dA, which is the pressure, minus rho v u. Okay, so this symbol basically is a tau turbulent. Okay, so the time average turbulent shear stress. Okay, this is the turbulent shear stress. Okay, in order to get the time average, let's say from here, the turbulent, we can put this one as the average equal to negative rho, okay, U and V. Okay, this is, you know that this is U and V represent the velocity fluctuating, right? Or we call it as a fluctuating velocity. Okay, velocity in this form. You can see here. You can see U, this one is a fluctuating velocity. So from here we do the average for the fluctuating, you will get the time average turbulent shear stress. Okay, so the total shear stress basically inside the pipe due to the laminar and turbulent effect. Okay, this is the shear stress only for the turbulent. For the total shear stress, tau, okay, will be tau from laminar plus tau from turbulent. Okay, tau for laminar is mu du over dy minus tau from turbulent is this one, rho u v average. Okay, so the shear stress can be related to the pressure gradient by summing the force on the horizontal cylindrical element. So now we need to apply again the this element, the control volume element, elemental approach. Remember that from previously we do the derivation of the laminar, we use the elemental approach. For this case also we use the elemental approach, but this one we neglect the inclination angle. Okay, so this is for the turbulent flow. Apply the summation of force in the x component equal to 0, because this y equal to 0 because the velocity profile is constant, there is no acceleration. Okay, so summation of force in the x direction, in this direction, positive, equal to 0. Okay, so what the force here? We have P multiplied with the area. P multiplied with the pi r squared. This is PA. PA is a force, positive. And this is negative, minus this one, the average, plus dP pi r squared, and then minus tau 2 pi r dx equal to 0. Okay, so this one, the weight is not considered because this is horizontal. This is, we have the weight as well. Okay, when we do the cos 0, it is 0. It is nothing. Okay, the weight is not acting in the horizontal direction. Alright, after this, we do the simplification. We expand pi r squared minus p pi r squared minus dp pi r squared minus tau 2 pi r dx equal to 0. So this one we can cancel. What do we have now? Negative dp pi r squared minus tau 2 pi r dx equal to 0. Okay, so here we can make the tau as the subject. tau average equal to, okay, I try to solve this one, negative R over 2, okay, dp average, this is dp average, yeah, over dx. Okay, so from here, this is the pressure drop. dp over dx is the pressure drop. So the pressure drop is already negative. So R over 2 can replace with delta P over L. Okay, because negative already mentioned the drop. So this is for the turbulent flow. So from here, we know that tau is equal to this, and previous tau equal to this. So what we need to do, the same again, we can equate both tau. Okay, the same thing. So we equate this one, I equate this one, yeah. So negative R over 2, the pressure drop, over dx equal to mu partial derivative u average over partial derivative of y minus u v average. This one, yeah. Okay, I do this one, equate this one with this one. Alright, so from here we can cancel this one, we can cancel this one, this become minus. Okay, remember that mu du over dy is equal to negative mu du over dr, because previously we discovered that the dr equal to negative dy, right? Okay, this is the same, so I want to replace this one with dr. Okay, so r over 2 dp dx, this is negative, negative with negative, okay, it will become positive. Alright, so from here, okay, I think therefore the final equation to be like this. This is the final form of, okay, velocity, sorry, the final form of the pressure drop, okay, the shear stress. Okay, you can see here. Okay, this is the final form. Okay, the quantity UV, this is the turbulent, cannot be determined analytically until the empirical expression is found. Instead of using the UV as the unknown, we often introduce eddy viscosity, this one. Okay, this is what we represent the eddy viscosity, this symbol. This defined by this relationship. U V average is defined by this eddy viscosity, du dy. Okay, and then from here substitute back into this equation. Okay, this equation we need to substitute into equation to 767. This one 767, and then we just substitute this one only. Okay, so R over 2 dp over dx equal to rho, this one, yeah, we replace with this one. Okay, du over dy, k minus mu du dr. Okay, basically this, okay, So this is not minus, this is positive, yeah, because this is positive. Okay, positive. So after this, we can do the factorization. You can see we have the we have the we have du dy. Okay. Okay. Y. Okay. So from here we can do the factorization. Okay, du over dy we can replace with du over dr. Okay, and finally we'll form this one. Okay, this one. Okay, so v plus v du over dr. Okay. So in view the turbulent process is a random and chaotic mixing of particle fluid, we may choose to introduce the mixing length Lm, the distance of the particle travel before interacting with the other particle. Okay, basically this term, okay, eddy viscosity by the definition is this square du, okay, dy, okay, where Lm is the mixing length. This is the particle moving in this direction, hitting another particle hitting another particle. Okay, so we say that the Lm is the mixing length before the particle hitting one another. So this is basically the average lah. Alright, so this is by the definition. And finally the correlation coefficient. Okay, this correlation coefficient represent the normalized. Remember, normalized is dimensionless shear stress. Okay, so K UV is basically by the definition is UV average over square root U square average V squared average. Okay, this is the shear stress coefficient correlation. Okay, I think that's all for today. This is the definition. Okay, for you to understand the eddy viscosity by this relationship with the derivation, all this. And I need you, okay, to study on your own. This is more on like reading. Okay, you need to read this. Okay, what is the velocity profile? Okay, for the hydraulic smooth. Okay, this one I already explained. This is more on the theoretical lah. Okay, so I will give to you, I will upload the complete versions of this one, fill up and share to you. Okay, this is just a reading. I believe once you read this one, you will understand about the roughness, because I already explained to you the roughness. This is the theory. Okay, so the next class I'm going to test your understanding. I'm going to ask you about this matter. Okay, about the velocity profile for the turbulent and laminar flow for both smooth and rough pipe. Okay, this one I give you homework to study first, and I will question later on. I will ask you during the next class. Okay, Okay, I think that's all for today. Thank you very much for your time. Okay, please revisit the lecture note. And in the meantime, I will release your result for test 1. Okay.
Thank you. Thank you so much, Doctor.
Thank you,
Okay.
Doctor.
Okay. Welcome.